So we have seen Z6 defined by these tables and Z5 defined by these tables. So they are both rings, but they have different properties. For example, in the case of Z6, there are some proper divisors of 0, such as this one. So 3 and 2 and 4. But in the case of Z5, there are no proper divisors of 0. So there are some differences and some similarities. And now we are going to characterize Zn for general natural number n. And to do so, let us introduce some definitions. And let R be a ring with an identity 1. So this 1 means it's not a number or integer 1, but it's an special element of this ring R, which we happen to denote by this symbol 1. And this acts as the multiplicative identity element of this ring. Okay, and let A be an element of R if this A is said to be invertible, if here's the definition, if there exists some element B in R such that AB is equal to BA is equal to 1. So this 1 is this one. Okay, or we say it's a unit. And in this case, we write B as A inverse. Okay, and we call this B as the inverse of A. Okay. Inverse of A. It's a multiplicative inverse of A, to be more precise. For example, the set of all rational numbers, the set of all real numbers, and the set of all complex numbers. In these sets, all non-zero elements are invertible. So for every element has its inverse as long as the element is not 0. Okay, and the set of integers has only 2 invertible elements. That is positive or negative 1. Other elements do not have any inverse, multiplicative inverse. Because, for example, 2, if there is any element B such that 2 times B is equal to 1, then B must be equal to 1/2. But this is not in this set. So it's not 2 is not invertible in the set of integers. And in the ring, Z6 has 2 invertible elements. That is 1 and 5. So these are invertible. This can be seen from this table of multiplication. So here is 1. 1 times 1 is 1. So 1 is its own inverse. And 5. 5 times 5 is 1. So 5 is its own inverse. So 5 inverse is 5, bracket 5. And 1 inverse is 1. And other elements do not have inverse. And in the case of Z5, there are all non-zero elements are invertible. Let's see. So from this table, 1 times 1 is 1, and 2 times 3 is 1, and 3 times 2 is 1, 4 times 4 is 1. So the inverse of 1 is 1, the inverse of 2 is 2, the inverse of 3, wait a minute, inverse of 2 is 3, inverse of 3 is 2, of course, and inverse of 4 is 4. So every non-zero element in Z5 is invertible. And here's another definition. A commutative ring in which every non-zero element is invertible is called a field. Okay, so the set of rational numbers, real numbers, and complex numbers, they are fields. And this Z5, is it a field? So every non-zero element in Z5 has inverse. It's inverse, but is it for this ring to be a field, it must be also commutative. So 1 by 1 is 1, 1 by 2 is 2, 2 by 1 is 2. So all we need to see is that if this matrix is symmetric, so 2, 2, 3, 4, 3, 4, 1, 1, 4, 3, 4, 3, 2, 2, 1, so it is commutative. So therefore this is a field. And the set of integers is not a field, obviously, because not all non-zero elements have their inverse. Now let us introduce one theorem which is almost trivial, so we don't prove it, but you can just examine this theorem. It's a characterization of a field. So let R be a non-empty set with addition and multiplication. Okay, so two binary operators. And suppose the following three conditions hold. This set R is an additive abelian group. Okay, additive means with respect to addition. Okay, and also R is actually R except for the zero element. In this case, this 0 is not the number 0, but it is a special element of R that behaves as the additive identity element. Okay, so this is the identity element of this additive abelian group. Okay, so except for this element, this set is a multiplicative abelian group. And 3, the distributive laws hold. So this means if A, B, C are elements of R, we have A times B plus C is equal to AB plus AC. And also A plus B times C is equal to AC plus BC. Actually, since we are assuming abelian for both additive and multiplicative groups, so only one of these is required. So if these three conditions are satisfied, then this set R together with addition and multiplication is a field. Okay, we don't prove this, just examine all the conditions and see these satisfy the conditions for a field. Now, here is a simple theorem that says every field is an integral domain. So this theorem almost looks trivial, but nevertheless, let us prove this. Okay. So what is an integral domain, by the way? The definition of an integral domain says it is a ring with an identity element with no proper divisors of 0. So let F be a field. Okay, then by the definition of a field, F is a ring, is a commutative ring. So the multiplication is commutative. Ring with an identity element. Okay, so this almost satisfies the definition of an integral domain. The only thing that is still lacking is that there are no, the absence of proper divisors of 0. So all we need to show is that there are no proper divisors of 0 in a field. Okay, so that's what we're going to do. So suppose A and B are elements of F. Okay, suppose, let's say, let A and B be elements of F, and suppose AB is equal to 0. Okay, 0 is the 0 element of F. Okay, it's not necessarily the number 0. Okay, this is just an element. Okay, 0. And now, if A is not equal to 0, then there exists its inverse, right? Such that A inverse A is equal to 1. Okay, so let's multiply both sides of this by A inverse. Okay, so A inverse AB is equal to A inverse 0. But this part is 1. And this part is 0. And 1 times B is B. So B is equal to 0. So that means B is not proper divisor of 0. And the same applies if we assume B is non-zero. So therefore, similarly, let's okay, just write the same thing. If B is non-zero, then we can show that A must be equal to 0. Okay, by a similar argument. By a similar argument. Therefore, F is an integral domain. And we are done. And the converse of this theorem is not necessarily true, but we have something similar. So, theorem. A finite integral domain is a field. Okay, so we need this finite in this case. Okay, to prove this, let D be a finite integral domain. So it's an integral domain, so it is a commutative ring with an identity element. Okay, with no proper divisors of 0. So what we need to show is it is a multiplicative group, abelian group. Okay, but abelian is okay because it is supposed to be commutative. Okay, so what we need to do is to show that it is a multiplicative group. I mean, D except for the 0 element is a multiplicative group. So this is what we need to show. So to show this, first we need to show that it is closed under multiplication. Okay, so if x and y are elements of D minus 0, then x, y is not equal to 0, right? Because x is not 0, y is not 0, and since D is an integral domain, there are no proper divisors of 0. So the product between x and y must be non-zero. Therefore, xy belongs to D minus 0. Therefore, closure condition is satisfied. And associativity is obvious, so so we just skip it. And what we need to show is that, so let's see, we need to show the existence of the identity element, but that is okay because it's an integral domain, so there is an identity element. And the last thing we need to show is the existence of inverse elements. So, and to show that, we will show cancellation property. Okay, so that is, suppose ax equal to bx with x being non-zero. Okay, from this we have ax minus bx equal to 0, and from the distributive law we have a minus b times x equal to 0. But since we are assuming x is non-zero and D is an integral domain, a minus b must be equal to 0. And therefore a is equal to b. So from here, we can cancel x. So cancellation holds. And from a previous theorem, if cancellation holds in a finite group, uh, in a finite semi-group, then that semigroup is actually a group. Therefore, D except for 0 is a multiplicative group. Okay, so let's say semi-group with cancellation property is a group. Okay, so this is a theorem we have proved before. Therefore, this is a multiplicative group. Therefore, D is a field. It's a finite field. And we are done. The next is a simple but an interesting theorem. So ZP, so this is the factor group of multiples of P. P is an integer, is a field if and only if P is a prime. So this is if and only if, so we have to prove both directions. So proof. First we prove only if part, and we prove this by contradiction. Okay, so suppose, so that means we prove if we deny this, negate this, then we prove ZP is not a field. Okay, so suppose P is not a prime. So this means there are some integers, let's say n1 and n2. So these are integers, and these are between 1 and P. And n1 times n2 is equal to P. So n1 and n2 are factors of P. Okay, and then their congruence classes are not equal to 0. Okay, but if we take the product of these classes, so by the definition of the product between congruence classes, this is equal to the congruence class of the product of integers. But n1 times n2 is P. But the congruence class of P is equal to the congruence class of 0. Okay, so therefore n1 or n1 and n2, these congruence classes are proper divisors of 0. Therefore, ZP is not a field. Okay, so it's not an integral domain, so it can't be a field. And next, if part, then suppose P is a prime. Then by these arguments, we can see that there are no proper divisors of 0. no proper divisors of 0. Therefore, ZP is an integral domain. Okay, but this is also finite. So ZP is a finite integral domain, but according to the previous theorem, a finite integral domain is a field. Therefore, ZP is a field. And we are done. Let's see a few examples. Consider the following simultaneous linear equations. That is 2x plus 3y equal to 1. Okay, in Z7. Okay, and 3x plus y equal to 4. So both we consider in this field. Okay, 7 is a prime, so this is a field. And let's multiply the first one by 3. So both sides are multiplied by this, and both sides of the second one is multiplied by 2. So that means 3 2 and 3 3y 3 1 and 2 3 and 2 y 2 4. Now since we are dealing with Z7, then 3 times 2 is 6 x, and 3 times 3 is 9, but in modulo 7 it is equal to 2, and 3 times 1 is 3, and this is 6x, and 2y equal to 2 times 4 is 8, but in modulo 7 it is equal to 1. So these two equations are inconsistent. You know, the left-hand sides are the same, but the right-hand sides are different. So there are no solutions. Next, consider again in Z7. In Z7, we consider the following simultaneous linear equations. 3x plus 6y equal to 6, and 4x and 5y equal to 4. So let's try to solve this, and let's see. So let's first multiply the first one by 4 and the second one by 3, so that we can eliminate x somehow. Okay, so we have 4 times 3, which is 12, in modulo 7 that is equal to 5, and 4 times 6, that is 24, in modulo 7 that is equal to 3, and again this is 3, and 3 times 4 is 12, in modulo 7 it is equal to 5, and 3 times 5 is 15, in modulo 7 it is equal to 1, so this is y, and 12, that is 5. So these equations are equivalent to these equations. So by subtracting this one from the first one, we have, so this will be eliminated, and we have, so 3 minus 1 is 2, even in modulo 7, and 3 minus 5 is negative 2. In modulo 7, it is equal to 5. Okay. So far, we have used only ring theoretic properties, and we did not use anything, any properties of a field. Now, we use, but this is a field, as we know. Z7 is a field, so every element has its inverse. Okay, so 2 has its inverse. But what is its inverse? And its inverse is actually 4. So 4 times 2 is 4 times 5. 4 times 2 is 8, but in modulo 7 it is 1. So we have, this is equal to 20, which is equal to, let's see, it's 7, so 6. So y is equal to 6. And from this, you can also show that x is equal to 4. You should verify this.